A single event, the Big Bang, has established our understanding of the vast and mysterious universe. However, what if this foundation of contemporary cosmology is incomplete? What if, beyond the veil of known physics, the universe conceals a secret history of cycles in which endings become beginnings, collapses become births, and so on? Go along with us as we unwind the texture of reality, investigating the provocative thought that the enormous detonation was not the start, yet basically a section in an unending vast story. The conventional account of how the universe began is one that most of us are familiar with. There was a vastly thick mark of limitless temperature and uncertain size called a peculiarity. This peculiarity detonated, making all the space, energy, and matter we know as our universe in an occasion called the huge explosion. Between \10 caret minus 36 and \10 caret minus 32 seconds, space extended dramatically, turning out to be a lot bigger. Space continued to expand after this point, but at a much slower rate, and in the end, we saw the universe we see today. This is the inflationary theory of the universe's origin, the most famous and broadly acknowledged hypothesis of how the universe started. However, this prevalent theory does not provide a complete picture of the universe's evolution, according to some physicists. Instead, they argue that the universe existed long before this moment and that it has continued to expand indefinitely into the past and future. The universe was shrinking before the Big Bang, whereas it is now expanding. The Big Bang is depicted as a rebound rather than a bang, the moment when a universe that was contracting shifted its course and began to expand. As per this hypothesis, the universe could return. The present development could be trailed by a breakdown in the far-off future, trailed by another bounce back. This rebound could be infinite, according to some physicists. Naturally, this goes against the majority of cosmologists' view that the Big Bang was the beginning of everything. However, it's actually significant that this hypothesis isn't the one in particular that thinks for even a moment to scrutinize the front line of cosmology. Brian Cox, a well-known physicist, has also questioned the Big Bang theory, asserting that nothing can arise from nothing. The James Webb telescope has made a number of unexpected discoveries that contradict the idea that the Big Bang marked the beginning of the universe, adding to the tension. If the Big Bang was and is not the beginning of the universe, then what is? All of these discoveries raise the question: is it possible that the universe began with a turning point or with something entirely different? Let's take a closer look at one of physics's most contentious ideas, the idea that the universe started out as nothing. Or, as it used to be known, the day without yesterday. Georges Lemaitre first proposed this concept in 1927. Even though it is still possible to argue that the universe may have started somewhere, this time in our universe's history had very little to do with the fiery Big Bang that started our universe. Even though some experts and some laypeople still hold that the Big Bang was the beginning of everything, this definition is out of date. The birth of time and space in 2023 was not the Big Bang of today. In point of fact, there is a lot of evidence that our universe had a non-uniform beginning. There is a limit. We have never reached temperatures this arbitrarily high. Instead, the best way to describe our universe is as a period of inflation before the Big Bang, and the Big Bang was a result of the end of inflation. During expansion, the universe is totally vacant. No particles, regardless, no photons, simply void space. This empty space has a lot of energy in it, and the exact amount changes over time by about 1 part in 30,000 on average. These fluctuations broaden to larger scales and produce new small-scale fluctuations above them as the universe rapidly expands and expands. The superposition of limited scope changes on middle-of-the-road scales and enormous scope superskyline scales is one of the characterizing prescient elements of grandiose expansion. As long as inflation continues, this phenomenon will continue, but it will stop at random and not all at once. In fact, if you lived in a universe that was expanding, you probably would find a place where inflation ended, and the distance between you and that place would grow exponentially. Before that region completely vanished from view, you might even be able to see for a brief moment what was going on at the beginning of the Big Bang. In a moderately little beginning district, maybe no bigger than a human-sized hamster ball yet presumably a lot bigger, the energy that was in space was changed over into issue and radiation. The conversion took about 10 to 33 seconds, which is short but not instantaneous. It happened quickly. The temperature begins to rapidly rise from a few degrees above absolute zero to around 20 Kelvin as the energy in space itself transforms into particles, photons, and antimatter. Everything will move at a speed that is close to the speed of light in the same short amount of time because there is such a large amount of energy being transferred. Whether the particle is massive or massless, every quantum will behave like radiation with some inherent kinetic energy. This progress is called warming and implies that expansion closes and the stage known as the hot enormous detonation starts. You will notice a significant shift in the expansion rate from any previous behavior. Space expands exponentially when the hot Big Bang occurs in an inflationary universe, with the most distant regions becoming ever further apart over time. However, the universe warmed up and the Big Bang began when inflation ended. The most distant regions are moving endlessly further away over the long run according to an outer point of view. The piece of the universe where expansion closes has a decreased extension rate, while the development locales encompassing it don't experience such a downfall. After a certain amount of time has passed under inflation, the distance to any object will double, and the distance will continue to double indefinitely. This procedure is never-ending. In any case, when the enormous detonation began, all that changed. From the perspective of the expanding region of space you were in prior to the Big Bang, it was likely that inflation would end numerous times in the vicinity as the universe's expansion slowed immediately. You would remain in the expanding region as a typical region of spacetime dominating its volume because the places where inflation ended would rapidly fill up with matter, antimatter, and radiation and expand at a slower rate than the regions that were still expanding. These hot Big Bang regions would quickly move away from all the other places where inflation continued at an exponential rate, which meant they would spread apart. Due to this change in the rate of expansion, it is unlikely that two universes with distinct hot Big Bangs will collide or interact in the standard inflationary picture. At some point, inflation will come to an end for us because our location is blessed cosmically. The energy innate in space itself will change into a hot, thick, and almost uniform ocean of particles. The main defects and deviations from consistency relate to quantum changes that existed and saturated the universe during expansion.